Okay. Hi, everyone. My name is Ryan Little. I'm a PhD student at Boston University. And so today I'm excited to talk to you about some work that's titled Private Account Recovery for an Anonymous Web Service. This is joint work with my great collaborators, Lucy Chin, my advisor, Mayank Faria, and also Scott and the rest of the Callisto team who you just heard from before. So as Scott has described, Callisto is a service which provides web-based services to survivors of sexual assault. And so Callisto's users have extremely high privacy needs. And so because of this, as Scott described, Callisto's backend doesn't store any identifiable personal information about its users. This includes their real names, usernames, or email addresses. So this is a really good requirement for privacy, but the drawback to it is that it makes it hard to do a lot of really common things that you would want to do on a web service. So this talk is going to describe how we were able to solve one of these challenges, namely the problem of account recovery. So if a Callisto user forgets the password associated with their account, how can we then verify them and let them regain access to their account without compromising their privacy? So account recovery is something that is pretty widespread on the web. Every website has this. For me, this is the only way I can get into a lot of my accounts. When you forget your password, you click on some forgot password button and you enter the email address associated with your account. The web service sends you an email that contains a one-time link. When you click on that link, you're brought to a page where you're prompted with some security questions, which you pre-chose back when you created your account. And then as long as you can answer those questions correctly, you will have regained access to your account. And the service will let you reset your password and regain access to all your data. So this is a system that works pretty well in practice, but it doesn't directly work for Callisto because the typical way of doing this is not private. You will just have the backend store some database of all the users' usernames, email addresses, and their security questions. All of this might reveal information about who they are. So our goal is how can we do some account recovery process privately? And so what we want is an account recovery that, first of all, preserves this same standard user experience, which I just described. And this is actually a very crucial goal for Callisto. And it comes from their focus on providing trauma-informed care. And so Callisto's users might be in a state of trauma when they're using the system, or they might be at risk of re-traumatization. And so part of what Callisto wants to do is to not add any additional undue burden onto the survivor. The system should be familiar and easy to use as possible. And it's because of that we want to stick with the user experience that is very common. We also want anonymity. So we don't want the server to have to store any user information on the back end. And finally, we want to use lightweight cryptographic primitives. And by this, I just mean we want to use crypto, which is fast enough to run in a web browser on JavaScript, because that's where the client is going to be running this protocol. So in designing the system specifically for Callisto, we have a kind of a unique set of design goals that we're trying to go for. So the first two are that we want the system to be cheap to maintain and easy to build. And so this is because Callisto is not a big tech company. They're a nonprofit organization. So we as cryptographers want to be careful with how we ask them to spend their resources, whether that's their financial resources or their engineering team resources. And as a sub goal of being easy to implement, we want to reuse existing code whenever we can. So Callisto has already built a lot of cryptographic code for the regular matching service, and we want to take advantage of that whenever we can to just reuse tools in our new system. And finally, we want to use standardized cryptographic primitives. By this, I really just mean we want to use crypto primitives that are implemented in widely available software libraries. So I'm now going to talk about an attack that we're really trying to prevent. So this is a dictionary attack. And so one of the worst possible outcomes for us is that some adversary is able to regain the entire list of users in the Callisto system. And one way they might do this is by a dictionary attack, which is where they have some list of email addresses or other information, and they just want to go one by one down that list and check if each one of these people has an account in the Callisto system. So with this attack in mind, I'm going to introduce 3 different threat models which are used to analyze the protocol. So we have one protocol, but we look at it under 3-threat models, and each of these are influenced by a different kind of attack that Callisto is concerned about. So the first adversary here is an external adversary. This is where there's some malicious client out there who's trying to probe the system and just gain information about who Callisto's users are. So we have this evil client on the laptop here, and then we have 3 Callisto servers. And so we're representing Callisto as this coalition of 3 non-colluding servers. In a practice, we can realize this by just having different servers, each protected by a different key, and each key is owned by a different Callisto employee. So this is actually our weakest of the 3-threat models, but we get our strongest security. So the external adversary actually isn't able to learn anything about the user list beyond users that the adversary created themselves or otherwise has access to. The next thing we look at is an internal adversary. And here we're trying to capture the threat that there might be a rogue Callisto employee or some coalition of rogue employees. So here we're assuming that at least one of the Callisto employees remains honest, but everyone else might be malicious, and they also might all be working together. So now it's actually possible for these adversaries to learn something about the user list. Namely, dictionary attacks become possible. But we're actually able to prove that essentially the dictionary attack is the best attack you can do. So you essentially have to run a dictionary attack to recover the full email list in this case. And furthermore, we can kind of mitigate the harms of dictionary attack by imposing rate limiting. So the presence of this one honest server can apply rate limiting on a dictionary attack, which is going to slow it down and potentially totally prevent it. Now, the third threat model we look at is a kind of interesting threat model, which is unique to our use case. So this is something that that Callisto's lawyers are very concerned about, which is that at some point, a court might issue a subpoena, which asks Callisto to disclose their entire user list. And Callisto wants to maintain its users' privacy even in this case. So here we're going to model this by having all the parties are now malicious and colluding, and there's no more honest parties. So now the malicious adversary can bypass the rate limiting. There's no more honest party that can oppose rate limiting, but we still have the property that the best attack you can do on the system is a dictionary attack. And the reason why this is okay is that Callisto's lawyers have legal reason to believe that a subpoena cannot compel them to do something that requires like an arduous amount of work, which includes a dictionary attack. So we have that the only way to get this dictionary or the only way to get the list of users is by a dictionary attack, and a subpoena cannot compel Callisto to run a dictionary attack. And so Callisto's user list is now protected against the threat of a subpoena. So I'm now going to get a little more technical and describe the framework of how our protocol works. And I'm first going to introduce a key building block, which is an oblivious pseudorandom function or an OPRF. So the setup here is we have a server on the right who has some PRF key, pseudorandom function key, and a client on the left who has some secret input. This is any arbitrary input. So the OPRF is some interactive procedure which lets the client evaluate that PRF on their chosen input. So the client learns this output and the server learns nothing. It is oblivious from the server's point of view. We like OPRFs for a couple different reasons. So first of all, they're concretely efficient. They're very fast in practice and they're easy to build. They also kind of naturally lend themselves to rate limiting, and that the server gets to decide whether or not they want to do this operation with any given client. So they can kind of naturally rate limit a client who has done too many requests by just saying, we're not going to do an OPRF anymore. And then the client's rate limited. And the third, and maybe the biggest reason we like OPRFs is that Callisto has already built them. So OPRFs, as Scott mentioned, this is a core part of Callisto's matching service. So they already have code to do this. So the way that our design uses OPRFs is like this. So during account creation, when the user is making their account and they want to prepare for future account recovery, they're going to engage with one of the recovery servers through an OPRF. And they're going to send as their input their email address and also some personal information string, which in practice means their phone number. So they do this, the user gets back some pseudo-random value, y sub 1, and the server learns nothing from this. the user is going to repeat this with all the other servers in the Callisto coalition. And by doing this, they get different pseudorandom values. And then they're going to hash them all those values together using some key-based password derivation function. And they get this key. So under this key, the server is going to, or the client rather, is going to encrypt all the information that the server is going to need to send that email with a one-time link. So they're going to encrypt their contact information and their chosen security questions. Now, this ciphertext is then just going to be sent to the servers, and the server is just going to store that forever. And so note that the server can't actually decrypt this ciphertext because none of the servers know the outputs of this OPRF, and so they can't learn the key, and so they can't decrypt this ciphertext. So now, what happens when the survivor forgets their password? So in recovery request, the user is essentially going to redo these OPRF interactions. They're going to resend their email and personal info string and rederive the exact same values from the OPRF. And now they can locally rederive the same key that was used to encrypt that ciphertext before. But this time, they can just send that key to the servers. And the servers can now decrypt the ciphertext which they've stored and learn the user's email address. And so this allows the servers to then send that email with a one-time link. So this is temporarily exposing the user's contact information to the servers. But the important part here is that the servers don't need to store that long term. They can send the email once and then erase it and forget about it. And all they have to do is keep this ciphertext. So this is only part of our protocol. We also have to do something similar for the security question answers, but that's beyond the scope of this talk. And so, it's not showing up. Okay, so this is the Callisto Vault login page, which Scott showed you before. And so you'll notice that we now, Callisto has implemented this protocol. So we now have this forgot password button down here, which allows users to recover their password in this familiar user experience. And the user never even needs to know that there is all this cryptography running in the background. So I'm going to leave you with a couple points. First, our work shows that private account recovery is possible and it's also practical. And secondly, I'm going to point out that our protocol can be used in any anonymous service. It's not just specific to Callisto, but it's very much tailored to the specific needs of Callisto and their users. And we see that specificity as a strength in our protocol. It's the specificity of the protocol, not the generality, which makes it able to run in the real world. And finally, I want to ask the question of what else is possible with anonymous web services. So what situations would necessitate the need for anonymity in a web service? And what other functionalities would we want to add or should we add to these systems? So this is not, I'm asking this genuinely. This is a question I'm very interested in. So if you also have thoughts about this, please come find me or send me an email and I'd love to talk to you about it. Now, the very last thing I want to do is I want to plug our Boston University graduate workers. We're currently on week 6 of our strike. We're fighting for a living wage, dental and vision insurance, and support for parents and caregivers. So there's a link to a support fund that you can donate to support our striking workers. And with that, I'm happy to take questions.